So the aim of this video is to give you some practice using proof by induction with integration. So here we have a definite integral. It has a label n, where n is a natural number but starting from 0, so I'm defining it to be 0, 1, 2, 3, 4, etc. And what I would encourage you to do is to try to use proof by induction to prove this on pen and paper, and then come back after you've had a good go at it and I'll go through a detailed solution. So I will see you in a while. Okay, welcome back. Let's look at the answer. So when you go from one sheet of paper to the next, that's a really good place for making mistakes. So it's a good habit to write out again what you're trying to show or what your last result was at the top of the page. And I'm doing it here on this slide. This is what we want to show. We're going to use proof by induction. Let's remember the format of a proof by induction. So what we should start with is, does it work for the starting value of our label n? And in our case, n's starting value is 0. So I want to see, does this work for n is 0? After all, it might be that somebody's made a mistake writing this out, and you spend some time trying to prove it with step 2 when it's actually wrong. So let's start off by checking it for n is 0. Afterwards, we will assume it's true for some value of n that I'm going to call k. And then, having made that assumption, we will see if it works for when n is k plus 1, the next value of n. So let's look at it for n is 0. So if we put n is 0 in here, we have the integral of sine to the 0, and that is the integral of 1. And the integral from 0 to pi of 1 with respect to theta is just pi. On the other side, we would have 2 times 0 factorial, so 0 factorial, times pi, divided by 0 factorial squared, times 2 to the power of 2 times 0, which is 0, so 2 to the 0. But we know, of course, that 0 factorial is 1, so these are just 1s, and 2 to the 0 is 1, so this is actually just equal to pi. So our formula holds for when n is 0. So let's move on the next slide to seeing if this formula can be shown to work. If we make an assumption that it does work for one value, can we show it works for the next value of our label? We'll do that on the next slide. So here I've written our assumption. This is exactly the equation we had before, but I've just replaced n by k. So k represents some arbitrary value that I'm assuming it is going to work for. And what we want to do now in proof by induction is to see if we make this assumption, will it work for the next value of the label? So let's write out the integral for the next value of the label. Let's be careful here because we've got a 2k there. So if we replace n by k plus 1, I'm just having this shorthand notation I of k plus 1 for our integral, then we're going to be integrating from 0 to pi sine of 2 times, and now k is replaced by k plus 1, so it's 2 times k plus 1. We obviously can't do this integral immediately, so what we're going to do is use integration by parts. And the standard way to do an integral like this would be to peel off one value of the sine, because that's something we can easily integrate, and we're hoping that we're going to then remain in the class when we use integration by parts, the class of integrals of powers of sines. So here is our same integrand, sine of theta 1 power times sine to the 2k plus 1. Remember here, if you expand that, it's 2k plus 2, so this is exactly the same. This factor here we're going to differentiate, we're calling it u. This factor we're going to integrate, we're calling it v prime. and this is the integration by parts formula. If you're going to use it, it doesn't hurt to write it out. So the integral of this is minus cos theta. We know that because if you differentiate cosine, you get minus sine. Minus minus is plus. We will get sine of theta. The derivative of this follows from the chain rule. We bring the power in front, 2k plus 1. We reduce the power by 1, so 2k plus 1 goes to 2k, sine of theta to the power of 2k, multiplied by the derivative of the function that was raised to the power. The function that's raised to the power is sine theta. The derivative of sine theta is cos theta. So now we just have everything ready. We just put it into this formula. So I of k plus 1 is going to be equal to, so it's u times v between these limits, and u is here, sine to the 2k plus 1, and v is minus cos theta, and I'm just going to put the minus sign in front, and this is between 0 and pi. Now, for whatever allowed values of k we have, 2k plus 1 is going to be positive, and the sign of 0 vanishes, so it's to some positive power, vanishes, and the sign of pi vanishes. The sign of pi to some positive power will also vanish. So therefore, this entire term is going to vanish. What about the second term in the integration by parts formula? So we have a minus sign, and then we're integrating from 0 to pi u prime. Now u prime has a 2k plus 1 factor in front of it. That does not depend on theta, so we can take it straight outside of the integral. So I'll put 2k plus 1 outside of the integral. We then have sine of 2k of theta written here, and there is a power of the cosine. And then that's multiplied by v, which is minus cos theta. So there is a minus sign here, and I'm going to take that outside immediately and make this plus. And then the power of the cosine times this power of the cosine gives us cosine squared. And that's the sort of thing when we're integrating powers of trigonometric functions that we really like to see, because what that tells us is we can replace this by 1 minus sine squared theta. And our class of integrals is powers of the sine function. So here we've got sine of 2k times 1, sine to the power of 2k times 1, minus sine to the power of 2k times sine squared. So this is a difference of two powers of sine functions. So our integral is equal to plus 2k plus 1. And now let's write this out in this type of notation. Sine to the 2k of theta times 1, when we integrate that from 0 to pi, is what we are calling ik. And that's very good because that's something we've made our assumption about. We know what that is. And then we have minus, and then it's sine to the 2k times sine squared. So that is sine to the 2, open brackets, k plus 1. And that's exactly this. So this is the integral that we are trying to calculate. So what we have is that the integral we're trying to calculate is 2k plus 1, open brackets because it's multiplying everything, ik, our assumption, minus the integral that we're trying to calculate. So we've now got an equation that we can rearrange to express the integral we're trying to calculate purely in terms of our assumption. So essentially, we're home and dry. So let's add this term to both sides, not forgetting that this term is multiplied by 2k plus 1. So on this side, we've already got one of these terms. Now we're adding 2k plus 1 of them here, close brackets. And on this side, we are left with 2k plus 1 times I of k. So this is 2k plus 2, or 2 times k plus 1, and I'm dividing both sides by it. Here we have 2k plus 1, and now here I am using our assumption to rewrite ik. So ik is 2k factorial times pi divided by k factorial squared and divided by 2 to the power of 2k. So let's look at the numerator first. If you've got 2k factorial times 2k plus 1, that is 2k plus 1 factorial. Think about what that means. The highest term in it is 2k plus 1, and it would then be multiplied by 2k, 2k minus 1, 2k minus 2, etc. So this product means that. On the bottom, we've got a power of 2, and we can multiply that into here, and that gives us 2 to the 2k plus 1. And we can take the k plus 1 factor and multiply it into one of these factorials to rewrite k plus 1 times k factorial as k plus 1 factorial. But we're left with a factor of k factorial because this was k factorial squared. So we've gone from here to here by rearranging, and it doesn't yet quite look like this, but let's have some faith in it, some confidence, and let's try and see if we can rearrange it and rewrite it as this, with k replaced everywhere by k plus 1. So how could we do that? Well, let's start on the bottom, on the denominator. If I want to rewrite this as k plus 1 factorial, I can do that as long as I say to get k plus 1 factorial here, I have to multiply it by k plus 1. K plus 1 times k factorial is k plus 1 factorial. And if I multiply the bottom by k plus 1, I have to multiply the top by k plus 1. So that's what I've done here. I've rewritten this as k plus 1 factorial, and in the numerator, I've put a factor of k plus 1. I then say I'd like this to be 2 to the power of 2k plus 2, because if I go back to here, if I replace k by k plus 1, and then I look at the power, I've got 2 times k plus 1, so that's 2 times k plus 2 times 1, so it's 2k plus 2. So I've got to multiply this by 2 to get the denominator I would like to have. And if I multiply the bottom by 2, I multiply the numerator by 2 as well, so that effectively I've multiplied by 1 and not changed this. So I've got this extra power of 2 here and an extra power of 2 here. So now the denominator is exactly this, with k replaced everywhere by k plus 1. K plus 1 factorial squared, 2 to the 2 brackets k plus 1. So what is the numerator? Well, we've got the pi there, and then here we've got 2k plus 1 factorial, remember we had that here, times k plus 1 times 2, and that is 2k plus 2. 2k plus 2 times 2k plus 1 factorial is 2k plus 2 factorial. Or, writing it slightly differently, 2 brackets k plus 1, close brackets factorial. This is just 2k plus 2. And that is exactly what we want to have, 2 times k plus 1 factorial. So, if I had a sheet of paper here, I would carry on and put one more line, but what I'm going to say here on this screen is that this is as expected, And what we say is, by the principle of induction, this is going to be true for all values of n. Because what we have seen on this slide is, if you assume it is true for an arbitrary label, it will be true for the next value of that label, of that parameter. Now, we've seen already from step 1 that it works when n is equal to 0. We now know it must work for n is 1. If it works for n is 1, though, it must work for n is 2, etc. So by the principle of induction, we conclude that this is true for all values of n, and that is the end of the proof. On the next slide, I'm just going to write a couple of very brief remarks about factorials, and with that I will then stop the video. So the sort of thing that we were using on the previous slide was results like this: n plus 1 times n factorial is n plus 1 factorial. And similarly, if you've got, say, n plus 2 times n plus 1 times n, you could write that as n plus 2 factorial divided by n minus 1 factorial. If you're not confident about that, I think exploring this sort of thing, writing the terms out here to see the cancellation that takes place to give you this, is a good thing to do. And with that, I'll stop the video.